Now for question number 1, we have aqueous solution of copper salt. Okay, you have this blue colored complex ion. This is similar that with the one that we have studied earlier. Okay, so this one, I think they didn't use the aqueous ammonia. Okay, do remember this reaction is going to be similar if you're using aqueous ammonia drop by drop. Okay, still the same. Okay, but here they said the reaction with aqueous sodium hydroxide. So write down the equation. So the one that is given in your marking key is this one. Okay, copper hydroxide. Okay, but I think we have learned about this as well, which is going to be this, instead of just simply writing it as copper hydroxide, okay, you can write it in this form. Okay, so the one that if you give your answer in this form also is correct. Okay, so the if you are going to give CuOH2 H2O4, okay, and then no charge, okay, plus 2H2O, this equation is also correct. Okay, because it's still going to give you the precipitation reaction. So this is a precipitation reaction. So it will be the color and the state of the copper containing product. So it's going to be a blue precipitate. Okay, so it's going to be a solid in solid form. Okay, it's going to be precipitate. So blue precipitate will do, no need to say blue solid. Okay, so here I think don't use this term. Okay, this is, I'm just using PPT over here for your class. Okay, but it's supposed to be blue precipitate, right in full. Okay, so to be exact, okay, in your textbook they mention it's going to be pale blue precipitate. Okay, so you choose which one you want to give. Okay, but it's supposed to be blue precipitate. Okay, it's not solution. Okay, blue precipitate. So next is going to be the reaction with the hydrochloric acid. Very easy also. Okay, you are going to get all the H2O, you remove, you get CuCl4 2 minus. Okay, so write the equation. Okay, this is going to be the equation, and then the type of the reaction is going to be a ligand exchange reaction. Okay, ligand displacement, if you want to use these kind of terms, it's up to you. Okay, and then the color and the state of the copper containing product, this is going to be yellow. This is not precipitation, it's going to be solution. So yellow solution. Okay, yellow solution. Now next is going to be this one, chloride ions can be identified using aqueous silver nitrate. So they have given you some a question where you need to do calculation. So if you read through this question, you say they started with this amount, okay, of this chloride of sulfur, okay, and then all the chlorine atoms present in the chloride of the sulfur are converted into chloride ions, okay. Then the solution is diluted to 100, so it means you have 100 cm cube of this sulfur chloride, and then 25 cm cube is taken. So please take note, you don't take everything, okay, you took only 25. Okay, 25 is titrated, okay, with 0.5 mole per dm cube silver nitrate. And then they have these results with silver nitrate. So what we can do is you can find out the number of moles of silver nitrate. So calculate that. Okay, so this one times, okay, and then divide by 1000, you get, this is going to be the number of moles. And I know, okay, every 1 mole reacts with 1 mole of this. Okay, so therefore my number of moles, okay, if I can, this is the number of moles of silver ions. So it means I can also find out that it's the same thing, okay, you have the same number of chloride ions, okay, but do take note, this is going to be 25 cm cube. So I need to convert this into 100 cm cube, so I need to times by 5, times by 4, okay. So it's 25, I want 100 cm cube, so times by 4, so I times this by 4, so that I can find out what is going to be the number of moles of Cl ions, okay, in 100 cm cube. Once I do that, I know that, okay, when you have the compound, okay, I just put SXClY. When they dissolve with water, you are going to get ion, S ion, and then chloride ion. I put X and Y over there. Why? Because of this X and Y over here. But okay, I need to find out, okay, related to this. Okay, so how do I find out? If I know the number of moles of Cl minus ion, what else I can find out? You can find out the mass of Cl minus. You can do that. Okay, how? Okay, number of moles equals to mass over mr or ar. Okay, in this case, if I want to find the mass, number of moles times mr. So this is the number of moles. I times with 35.5. I can find out, okay, the mass of chloride ion. Okay, mass of chloride ion. So I have 0.159 gram. So we know that this sample, okay, 0.303 sample, they have sulfur ion and chloride ion. So you found out for chloride ion, so you can find out the sulfur ion, okay, which is going to be just minus. Okay, when you minus, you will get the mass of sulfur ion. So the rest, just put it over here, okay, like table, like what you always do. Okay, 0.144 gram, then 0.159 gram, okay, the one that you calculated, divide with the AR, okay, or in this case, the relative formula mass, okay, and then once you get this, you will get this 4.48, which is the same as this, which is, okay, and then the sulfur, when I do that, get 32.1, okay, I get 4.49 times 10 negative 3 also, okay, so I will get the ratio 1 to 1. Okay, what does it mean 1 to 1? The empirical formula is going to be SCl. Okay, so this is to get that 3 marks, okay, you need to go through all this kind of working. Okay, please take note. The important thing, or maybe the confusing part, is this part, the mass of ion. Okay, we normally don't find the mass of ions, okay, normally, okay, but in this case, yes, we need to find. Okay, next. Okay, that's group question number 1, 9 marks. Okay, 9 marks. You see testing on what? Okay, just on the equation and then calculation. Okay, not bad actually for 9 marks. And then for number 2, okay, this is also theory based. Group 2 nitrates decompose when heated. So when they decompose, they give you metal oxide, nitrogen dioxide, and oxygen. So you need to know about this. If no, you are not going to be able to balance it. Okay, so using that, you just balance, okay, and then you will get these numbers over there. Okay, once you balance, okay, then it's fine. Okay, you will get that 1 mark. B, describe and explain how thermal stability of nitrates changes with increasing atomic number. I think why they use increasing atomic number rather than using why going down the group. I think when we say going down the group, students will tend to use the increase in shell. Students may tend to use shielding effect. Okay, so to prevent that, I think they are using this increasing atomic number. Okay, but you need to know which one you need to focus. Okay, to give the answer. Okay, so in this case, we know the thermal stability of group 2 nitrates. The stability is going to increase. Okay, stability is going to be increasing. Okay, let me check whether you guys can. Okay, I'll share the screen again here. Okay, let's continue. So here, okay, the thermal stability, okay, is going to increase. Okay, and then why? Because as you go down the group, okay, when you go down the group, cationic radius, okay, the cationic radius, it means we're talking about group 2, the cation, the radius is going to increase. When the radius is increasing, okay, you are going to get less polarization, okay, or less polarizing ability towards the nitrate. Okay, so less polarizing ability, or you can say the electron clouds are going to be less distorted. Okay, so because of that, okay, because of that, the thermal stability will increase. It's going to be more stable. Okay, so it means it's difficult to break the bonds between the nitrates. Okay, so please utilize, okay, everything over here. I think the same thing that we always use here is the cationic radius. Okay, cationic radius. Now, C. The variation in the thermal stability of group 2 amides are the same as the group 2 nitrates. This is important because they are testing something that is not in the syllabus. Okay, because we don't actually look into the thermal stability of amides. Okay, but they already say it's going to be similar, so we just need to evaluate only. Okay, so we learn about carbonates. Okay, we learn about nitrates. Okay, so now they are extending it to amides, but they are telling it's similar. So the moment they say it's going to be similar, okay, that is going to they're telling use the same knowledge, okay, that you have, okay, and then relate them to this, okay. So suggest, okay, whether calcium amide, okay, will decompose more or less readily than barium amide. So I want to suggest, okay, I know the barium is lower, calcium is at the top, okay. When calcium is at the top, it's smaller, okay. The cationic radius is going to be smaller, and then because of the smaller ionic radius, okay, calcium, and then greater charge density because of that, okay. So because of these two, okay, greater charge density and smaller ionic radius, this is going to make, okay, the polarizing power to be greater, okay, for calcium. So it is going to be more readily, okay, the calcium amide will be more readily decomposed, okay, because of the small ionic radius or greater charge density. Okay, you just explain. And then this compound decomposes when heated to form, okay, these two. So you need to write the equation. So just simply write the equation and try to balance. Okay, I'm not going to teach you how to balance. You need to do it yourself. Okay, learn. Now, the next question is, you have this ion, okay, NH2 minus ion. Do remember nitrogen has 5 valence electron, okay, but since there's going to be another one more electron over here because it's ion, okay, so therefore you are going to have different combinations of the lone pair and bonding pair. Okay, so if you look at the, when we say predict the bond angle of NH2, okay, if we predict the bond angle of NH2, okay, explain the answer using this. So when we have nitrogen, okay, just nitrogen alone, so one of the electron is used here, another electron is used here. So you might have 3 more electrons because nitrogen have 5 valence electrons. So because of the NH2 minus, therefore there's another one more electrons over there. So because of this, you are going to get 2 lone pair of electron and 2 bonding pair. Okay, because of this, we are going to have, okay, the bond angle which is similar to water. Okay, so therefore, okay, the bond angle is going to be 104.5 degrees. Okay, that's going to be the bond angle. So explanation will be, you need to mention about, okay, the 2 bonding pair and 2 lone pair. You need to mention about that. And you need to also mention that the repulsion, okay, between the lone pair and lone pair is greater. Okay, and that will make the bond that we measure over here. Okay, the repulsion over here is going to be greater. So this bond is going to be, the bond angle will become smaller, okay, than expected. Okay, so please remember that. Okay, answer key, they do accept, okay, 104 to 105 degrees. Okay, so that is the, okay, we will continue. Okay, so you have this chloride 5 ions are powerful oxidizing agents. Okay, they mentioned that they are powerful oxidizing agent. So if they are powerful oxidizing agent, they are going to oxidize others, but at the same time they are going to get reduced. Okay, when they are going to be reduced, okay, do remember oil rig, okay, reduce is gain of electron, they are going to be gaining electron. So this is going to be important because later when we want to try to balance the equations, okay, it's going to be very important. Now, here they mentioned that if the reduction, okay, of this ion, okay, SO2 forms CaO2 and sulfate ions as only products. So you need to balance the equation. Now, for any equation related to redox, okay, I will strongly advise you to do it in a half equation. Okay, don't balance it directly. So let's do the half equation. So if I put it in a half equation form, okay, so you see ClO3 minus, okay, they are going to be forming ClO2. And do remember, this is going to be a powerful oxidizing agent. It means that they are going to gain electrons. So just in case, I'll just put it over there. Okay, they are going to gain electron. It's okay, Aneta, no problem. So here, okay, if you have the gain of electron, and then the second one is going to be the SO2 is changing into SO4 2 minus. Okay, so if this one is going to be something is gaining electrons, so of course here will be okay, plus electron here. Okay, so anyway, okay, we try to work using this first. Okay, you see here, the first thing is they say that there is the only product is going to be ClO2 and SO4 2 minus. But if you want to balance this, there is no way just simply balancing this with the existing elements or ions. Okay, why? Because you can see the ClO3, okay, minus, and then you have ClO2. So there is another one more oxygen that is missing. So you include that oxygen in form of water. Okay, you include in form of water. And when you include that in form of water, then you include here H plus. Okay, you include H plus, and then you try to balance this up. Okay, because you see H2. Okay, so everything is balanced except for hydrogen. So I will include 2 there. Okay, and then okay, we try to balance the electrons. Okay, the electrons, how many electrons should I add? You see here on the my product side is going to be 0 charge. And then at my reactant, okay, I have -1 and then 2H plus, so it means +2. So I have total charge of +1. I want to make it left and right, okay, must be the same charge. So what I need to do, I need to add 1 electron, okay, 1 electron, so that I have the plus -1, so that you get 0. Okay, so that is going to be to determine how many electrons should I add. Okay, now let's move on to the second equation. This is equation number 1. So second equation, SO2 to give you SO4 2 minus. So similar, we know that water is being formed, but water must be cancelled because they mentioned that the only product is ClO2 and SO4 2 minus. So of course water needs to be cancelled. So I need to put, okay, H2O over here. Have to, no other choice. Okay, so if I put the H2O, and then I want 4 oxygen, so the best way is to put 2 here. Okay, and then there is no H plus here, so I need to put H plus, and then there are 4 H plus. Okay, if you come over here, 4, and then the last one is to balance the charges. Okay, the charges you see here, the charges are 0. And then if you see the charge here, -2 plus 4, it's going to be +2. But I need to make sure left and right are 0. Okay, according to what we have over here, must be the same charge. Okay, so 0, and how to make it 0? +2. I need to plus -2. How do you get -2? By adding with 2 electrons. Okay, you add with 2 electrons. So now the charges and everything, they are balanced. Okay, so left with just adding all of them together. Okay, but okay, we need to make sure the electrons are going to be balanced as well. Okay, so what we do, okay, 2 electrons and 1 electron, you need to times everything by 2. Okay, so times by 2, 2, this will become 4, 2, and 2. So when you add, okay, this water will cancel. When you add, the H plus will cancel. The 2 electron will cancel. So this one will look like what they mentioned. You are going to get something where there is no other products that is going to be formed. Okay, so you will get this. So your work is just to put it over here, and that's going to be your answer. Okay, so that is how you balance, okay, by using the information here, okay, and then try to balance. Okay, now the next question is going to be chlorine dioxide. Okay, disproportionates with hydroxide ions, okay, to form a mixture of ClO2 minus and ClO3 minus ions. What is meant by disproportionation? Disproportionation is going to be the same substance has been both oxidized and reduced at the same time. So we that is our explanation, but you still need to mention about using this reaction example. So you need to calculate the oxidation number to show, because not enough by just explaining oxidized and reduced. So on based on what you know that they are going to be oxidized and reduced. So based on what? Okay, so you need to calculate the oxidation number. So let's calculate the oxidation number of Cl in ClO2. So this is x, okay, minus 4, 2 times negative 2 equals to 0, x equals to 4. Okay, you can see 4 and 4. So now let's say I'm going to calculate for Cl over here. So x minus 4, okay, equals to negative 1, x equals to negative 1 plus 4. I'm going to get plus 3. So this is going to be plus 3. So this is going to be ClO2 to become ClO2 minus. Okay, you are going to get this. Include that information. Okay, this is going to be reduction. So the next one is going to be this. So you just put x minus 6 equals to negative 1. So x equals to negative 1 plus 6. So it's plus 5. So this is plus 5. Okay, so this one is going to be ClO2 to become ClO3 minus. So this is going to be oxidation. So make sure you involve all this information to get that 1 mark. Okay, you need to calculate. If you don't calculate, okay, forget it. Okay, you are not going to get the 1 mark. Okay, deduce the ionic half equations, okay, for the reaction in B1. Okay, so deduce, okay, this one is going to be, if you want to deduce this reaction, just put, okay, because ClO2 to ClO3 minus, okay, ClO2 to ClO3 minus, okay, that's the equation. And then I also have another equation, which is going to be ClO2 to become ClO2 minus, okay, this equation. So how do I deduce the half equations for that? Okay, quite simple also. You see here, when you have this ClO2 to become ClO2 minus, okay, we know that this is going to be reduction. Okay, reduction is going to be gain of electron. So when I see here, there's nothing changed, ClO2, ClO2. So I just put gain 1 electron. So you get minus. No need to add anything. Okay. So that is going to be how did I end up with this half equation. Very easy. But the second half equation maybe need to do extra stuff. Okay. What is the extra stuff that I need to do? Okay. Because there is ClO2 and there is going to be ClO3 minus. Okay, there is going to be one more extra oxygen. Okay, one more extra oxygen. But again, they say deduce. Okay, don't simply do something new. Yeah, when they say deduce, okay, you see this reaction automatically changing into this. So another reaction is there is an involvement of OH. Okay, it means there is ClO2 is reacting with OH. Don't go and simply put, okay, ClO2, ClO3. So here must have water. Don't do that. Okay, don't do that. Okay, cannot just directly use the one that we always use. So this one is deduce. So you deduce using what you have, OH. You add OH here. Okay, you add the OH here. And when you add OH, okay, what is going to happen? You are going to get, in this case, must get water. Okay, because in the previous equation, there is no water. So I included water. And then I try to balance. Okay, I try to balance because if I put water over there, I'm going to get 4 oxygen. But now I'm only having two oxygen. So I need to make sure I have 4 oxygen. So I put 2 OH minus. So when I put that, my hydrogen also will be balanced. So the only thing that I need to balance now, okay, because the charges, you see, the first equation, the charges is going to be -1. This is -1, it's okay. but the charges over here is going to be 2 negative, so -2 on my left hand side. The charges over here on my right hand side, this is 0. Okay, so this is -1. So I need to make sure my charge, okay, on my left and right is going to be the same. So it's -2. The only way to make it -2 is going to be by adding another electron here. So I'm going to get plus -1. So I get -2. Left and right is balanced. So that is where I get this equation. Okay, deducing. So maybe this equation easy. Maybe this one might be confusing. Okay, but I already told you how to get it. Yeah. Now, next is going to be a lithium iodide electrochemical cell can be used to generate electricity. They have this lithium electrode and inert electrode immersed in body fluids. Okay, when the current flows, lithium is oxidized and iodine is reduced. Okay, use the data booklet to write the half equation for the reaction taking place at the two electrodes. Okay, so they mention half equations. Don't go and write standard reduction potential. Okay, so it means you need to tell which one is oxidized, which one is reduced also. Okay, you need to adjust accordingly. So hence write the overall equation. So I know now they say lithium is oxidized. So it means lithium, okay, you are using lithium. So lithium is going to be oxidized to become Li plus. Okay, so I just Li, how Li can become Li plus, because Li plus is group 1. Okay, so Li plus, so you lose electron. So you lose electron, so I put the plus electron on my right hand side. And then another one is iodine is reduced. So I2, okay, is 0. So reduce means, of course, I minus. Okay, so it means it must be 2 minus, also 2I minus. So I just put it over here. How do you get from neutral to become I minus? So plus electron. So how many electrons? 2 electrons. So I put it already. And then write the overall equation. Yeah, so you need to put the 2 2 2 to cancel the 2 electron, and you will get the overall equation as this. Quite easy. Yeah, quite easy. When I look at the, okay, my data booklet, this is the standard reduction potential that I will get. Okay, Li plus plus electron to give you Li negative 3.04. And then I2 plus 2 electron, okay, 2I minus, positive 0.54. This is very important because, okay, now I know, okay, which one is more positive. I know that 0.54 is more positive. This will go forward and this will go behind. So when it goes behind, this one will become positive 0.3, positive 3.04. So when they ask you to calculate the E cell, I will calculate the E cell, okay, using this method, because this is moving forward. Since this one is moving forward, so 0.54 positive. This one is going to move backwards, okay, so it's going to be plus 3.04. So when I add this, I'm going to get 3.58. So when you write down, make sure you write positive 3.58. Next, a current. Okay, a current is going to be drawn from this cell. So this is the current. We are going to calculate the time taken, okay, for the 0.1 gram of lithium electrode to be used up. So basically Li plus plus electron to give you Li. Assume the current remain constant throughout this period. So here, first of all, if you have 0.1 gram of lithium, calculate how many moles first. Okay, so when I calculate this one, you get it from your periodic table 6.9. Okay, you will get this number of moles. And then, okay, when you look at the charge, okay, Q equals to IT. Okay, so you just put, okay, the current with the time in seconds. Okay, in seconds, that's going to be the current. Okay, that's going to be the charge. Okay, that is going to give you 0.1 gram of lithium. Okay, So based on what I have over here, this one we have learned every 1 mole, okay, every 1 mole of this 1 mole of electron. So we call it 1 Faraday, the charge, okay, for 1 mole of electron is going to be 1 Faraday. So that 1 Faraday is supposed to give you 1 mole of lithium. So I just put there. So 1 Faraday, I know the charge. Okay, this one we normally memorize 96500. It's going to give you 1 mole of lithium. Now I don't have that column. Okay, 96500. Okay, so I do not the column that I have, okay, is going to be I need to find out what is going to be the column that I have, okay, because if I have 1 mole of lithium, then 96500, okay, but now I don't have 1 mole of lithium, I have this amount of mole. Okay, so what I do is I just need to times this by 0.01449. So this one also you times with 0.01449. Okay, and you will get the column. Okay, you will get the column, which is going to be, if you do that, you are going to get this value. Okay, so where do we get this? Okay, you are going to get, okay, you are going to get from 96500. Okay, you times with 0.01449. That is going to be the column, and that columns that is going to be related to this. So you just need to put 1398.55 equals to 2.5 this and time, calculate the time in seconds. Okay, this is going to be the seconds. When I calculate, I'm going to get this. Okay, I'll stop for a while for any questions. Charlton, okay. Can I hear you, Charlton? Everything okay?
Yeah.
Jason, is everything okay? Can follow? This is okay. Yeah, this question is quite okay. I think the one that I find it challenging a bit is the one that we did earlier, where we need to use the calculation to prove for Avogadro constant. Yeah, that is something that is very interesting. Okay, this one is still okay. Okay, so please practice on this. Okay, generally that's going to be 3 marks or 4 marks maximum. Okay, so please remember how to use this. Okay, it's one of the very popular questions, okay, in your paper 4. Now, so let's move on, okay, to question number 4. Sketches of the shapes of some of the atomic orbitals are shown. Okay, so identify the type. So you have sp or d. Now d we don't really study, okay, but we have learned about s and p. So of course the another one should be d. So you see s is going to be spherical, okay, so therefore this is going to be s. P is going to be a dumbbell shape, okay, so it's going to be P, and then left with one more, it's going to be D. Okay, so cadmium forms the 2 ions. Okay, they have given the 2 ions and the electronic configuration is given. Now use this information to explain why cadmium is not a transition element. So talking about the definition of a transition element. Definition of transition element is going to be an element that can form one or more stable ion. Okay, one or more stable ion with incomplete D subshell. Okay, with incomplete D subshell. So whenever you see here, the D subshells are all complete. Okay, so this cadmium is not a transition element because, okay, the D subshells are complete for both of the ions. Okay, D subshells are complete. Or you want to just use, if you want to use this approach, you say that, okay, cadmium is not a transition element because it doesn't form one or more stable ion with incomplete D subshell. Okay, so different ways of answering. C. Methylamine is a monodentate ligand. Okay, state what is meant by the term monodentate in this context. Monodentate means, okay, it has one lone pair that can be donated to metal ion. Okay, so because we don't say donated just like that, you can just say methylamine, okay, can form one dative bond, okay, one dative bond by donating one lone pair to the metal ion. Okay, so what is meant by monodentate? Okay, so monodentate donates or forms one dative bond with metal ion by donating one lone pair to the metal ion. Donating or forming a bond by donating one lone pair. Okay, depends, okay, how you want to put it. Okay, but do remember, okay, the dative must be there, lone pair must be there. Okay, but in this question I think they only focus on the lone pair, but the marking key, okay, will be a little bit more flexible, so they will say they'll accept one dative bond or one lone pair, still fine. Okay, so that is going to be the answer for this monodentate ligand. So in the presence of aqueous methylamine, okay, this one reacts with to form a mixture of two isomeric octahedral complex. Complete a three-dimensional diagram to show the isomer. So they are asking you to use L to represent the CH3NH2. Okay, so it's a monodentate. It means each one is you are going to have one L. Okay, each one is going to be one L. So the only thing that can exist over here is going to be cis and trans. So one is going to be side by side, another one is going to be opposite. So you can just draw, okay, side by side, and another one is going to be opposite, but just be careful, okay, H2O, the lone pair is coming from oxygen. So when you write H2O in this form, okay, write down OH2, okay, or you can also write it in this way, it's also okay, fine. Okay, as long it is going to be, it looks like it's connected to oxygen. And very important, okay, some students always ask, can I just simply use this? Don't. Okay, always use this method. If you don't show the 3D dimensional diagram in this way, you are going to be deducted mark. Okay, the two triangle that appears to come out, okay, that is actually coming out from the piece of paper. The two lines over here, this is assuming that it is going behind. Okay, so this is going to be cis, this is going to be trans. Next question, state what is meant by the term stability constant. Okay, stability constant is like something like Kc. So it's an equilibrium constant for the formation of a complex ion in a solution. So like for example, in this, okay, it's like something like Kc, okay, but we are not going to involve water. Okay, we are not going to involve water. So this one divided by this to the power of 4. Okay, so that is going to be K step. Okay, stability constant. Complete the table by placing one tick in each row to suggest how increasing temperature will increase the K step or how it will affect the K step. Do remember, temperature only will affect K step or any Kc. Pressure, pressure, concentration will not affect, okay, K step or Kc. And the equilibrium concentration of cadmium complex. Okay, quite simple, okay, because this is going to be negative. Okay, if it is negative, I told you to put your hand and then just put it's hot. Okay, so this one, put your hand, this is going to be cold. So when I increase the temperature, I am going to I need to decrease the temperature. How do you decrease the temperature? By moving from hot to cold. So the position of the equilibrium is shifted to the left. Okay, so it depends on how you answer the question over here. So here, okay, the K step is going to decrease. Why? Because you are going to form more reactants. Okay, so it's going to be, it's supposed to be this, okay, divided by this. Okay, of course, this one, if it is this one is decreasing, the entire K step will decrease. And then they also ask about the concentration of this ion. So since it's moving backwards, so of course it's going to be decreased as well. Okay, so explain your answer. Okay, higher temperature will favor what type of reaction? Okay, higher temperature will favor, this is going to be exo. So they are going to go behind. So it's endo. So higher temperature favors endothermic reaction. And therefore the reaction, okay, moves backwards. Okay, or the position of the equilibrium shifted to the left. Okay, so if you mention that, you will get a full mark. In the marking key, they say that the forward reaction is exothermic. That's why, okay, higher temperature will go backwards or something. But it's still the same answer. Temperature is high will favor endothermic reaction, which is going to favor the backward reaction. The moment you mention that, you will get the solid 2 marks. EDTA 4- is a polydentate ligand. When a solution of EDTA is added, a new complex is formed. So here you have two stability constant. So a solution containing equal number of moles, okay, so they are giving equal chances for the competition of this ligand exchange. So they are telling predict which complex is formed in the larger amount. Okay, this one you just need to focus on the higher K step. Okay, so the one that is going to be formed more is going to be 10 to the power of 16. So it means the EDTA ligand is more stronger, okay, compared to the CH3NH2. Okay, so this is going to be the EDTA that will give you the 10 to the power of 16. Okay, it's going to be formed in a large amount. So to explain that, explain your answer, just tell, okay, this one, okay, because K step is higher than the other. Next question, methyl amine is a Bronsted-Lowry base. Okay, Bronsted-Lowry base is going to be, they say Bronsted-Lowry, they say it's a proton acceptor. Okay, any base is a proton acceptor. So methyl amine is going to be a proton acceptor. So you need to think about in that perspective. Write an equation to show methyl amine dissolve in water to give an alkaline solution. So I just put this one, okay, plus with water, okay. Water will have H plus and OH minus. So I was thinking that is a proton acceptor. This is proton. So H plus will go and join here. Okay, so you are going to get CH3 and H3 plus, and then left with OH minus to show that it's an alkaline solution. Now, initially I put the arrow as a single arrow, but when I check in the marking key, they put a double arrow over there. But for me, okay, since they just say write an equation and they didn't mention that the reaction is going to be reversible, there is no way for us to deduce that it's going to be reversible. So for me, okay, if you just give your answer without the presence of the double bond, it's still correct. Okay, but okay, if this one you want to learn, okay, it's going to be a double reversible reaction, then you include. Okay, but here if you give a straight line to form, okay, like for example one arrow like that, then I'm fine with that. Okay, this is I'm fine with that. Okay, you will not be deducted mark. Now, next question is methyl amine is a useful reagent in organic chemistry. So construct an equation, okay, for the reaction. They didn't say must follow what kind of equation. So anytime whenever I'm dealing with organic compound and then they ask me to write an equation, the best way to see is by using structural formula. Okay, this one I've seen many times. Don't use the full formula, like for example, C2H3OCl. No. Okay, it is much more easier if you can represent using structural formula. This is ethanol chloride. and this is going to be methyl amine. Okay, methyl amine. And then what will happen? The hydrogen, one of the hydrogen will join with the Cl to give you HCl. So the rest is CH3CO, and then they will join with this and one of the hydrogen here. Okay, so the nitrogen. Okay, they will join with the nitrogen. Okay, so when they join with the nitrogen, so left with this. So that is going to be the equation. Methylamine also reacts with propanol. Okay, this is propanol. It's a carbonyl compound. Now, carbonyl compound, by this time, because you are in A2, you should know carbonyl compound, they always have this mechanism of reaction, which is going to be nucleophilic addition. So that it will be something that will be playing in my head. Okay, maybe they are asking about nucleophilic addition. Okay, but don't simply just give your answer. You need to analyze properly. When this reaction is happening, I am going to get, okay, this P. Okay, but if I want to deduce the type of the reaction over here, okay, the type of reaction is going to be, I can see that water is being removed over here. Okay, if water is being removed over here, the I think the type of the reaction, it can be also written as condensation reaction. Okay, because water is removed. Okay, but the best answer is not condensation. The best answer is going to be it's a very special type of reaction, because generally we think it's a nucleophilic addition reaction, but it's a very special. Why? Because first of all, okay, when I have CH3 CH3 double bond O, what happens is going to be the double bond O, okay, there will be, they will change into, okay, because it's more electronegative. Okay, so you are going to get CH3 CH3, and then O minus, and then one is pending. Now this O minus, they will join with one of the hydrogen here. Okay, one of the hydrogen here, so they will give you OH. And then the remaining compound, they will come and join over here, which is going to be N, remaining with H, and then CH3. Okay, you are going to get this compound. Now, this compound is not going to be stable. Okay, why? Because you need to form this. How that thing is going to be formed? The OH and H will be removed. Okay, this is going to be the dehydration. Okay, dehydration. So they are going to give you the double bond between the carbon and nitrogen. So carbon and nitrogen double bond. The OH and H is removed in this way. So here, okay, what type of reaction that is happening? Number one, because new bond is being formed, okay, with this compound, the nitrogen compound. So that is going to be already addition. Okay, that is going to be already addition. And the last one, when I'm trying to remove, okay, rather than saying it's going to be condensation, you can just put it as elimination. So there is a type of reaction that you need to know, which is addition elimination reaction. Okay, addition elimination reaction. Very rare they ask, but when they ask, yeah, they really want to test on this term, addition elimination reaction. Very, very popular. Okay, so far I've seen 3 questions asking about mechanism involving addition elimination. And also you need to know how to use this way of drawing using curly arrow diagrams and so on. Okay, but for this question, 13 marks. Okay, done. So let's look at the question number 5. Okay, before we go, any question for question number 4? Okay, let me check the chat. Okay, no problem. Yeah, so here, okay, if you have question number 5, you see chloride 1 ion undergo the following reaction under aqueous condition. The series of experiment was carried out at different concentration, and the table shows the results obtained. Use the data in the table to determine the order of the with respect to each reactant. So this one is quite simple. Okay, why? Because when you want to find out the rate of reaction, okay, the rate equation, you just compare. Like for example, I see that, okay, when I put from there must be one one concentration must be constant, okay, so that I can measure. Like for example, experiment 2 and 3, I know that these two, it's constant 0.4 and 0.4. So when I double this, okay, when I double this, what will happen here? Okay, you can see from 2 to become 8, this is going to be times by 4. So this is similar to times by 2 to the power of 2. Okay, so you can see this is going to be a second order reaction with respect to ammonia. So I put second order. And I also need to find out related to ClO minus. So how do I find out? Okay, I need to look, first of all, look whether, okay, ammonia is going to be constant, but I don't see any of the ammonia concentration is going to be constant. So you still need to use the basic assumption that, yeah, ammonia is going to be the second order reaction. So I'm going to use that to find out. So how to find out? Okay, we know that from here to here, okay, is going to be times 2, and here to here is going to be times 4. Okay, 1 and 3, yeah, I'm talking about 1 and 3. So from here to here is going to be times what? So I need to find out. Okay, so 8.2 divided by 0 0.256. Okay, 8.2 divided by 0 0.256, I'm going to get 32. Okay, 32. And I know, okay, and I know that ammonia is going to be second order. So if this is going to be times by 4, this is going to be supposed to be times by 4 to the power of 2, which is going to be 16. So 32, okay, is going to be 16 times what to give you 32? Okay, because I want to get 32. So 16 times what to get 32? 16 times 2, you will get 32. Okay, and that 2 is coming from where? That 2 is coming from here. When you times by 2, then it's going to be times by 2. Okay, this part. So it means that, okay, if times 2, it means basically this one is going to be first order with respect to ClO minus. Anyone don't understand this explanation? Jason, can you understand this explanation why it's going to be power of 1? Jason? Jody, can you understand this?
The for ClO minus, yes.
Which one? Yeah. How do
I
you
don't.
know that it's going to be, how do I know that this is going to be 1? Okay, if you don't understand, okay, I can also show you using different experiment combo. Okay, if you are using different experiment combo, maybe we don't use the 32 you see here. If I want to use different combo, okay, maybe I use 2 and 3. So now maybe I use, just now I use 1 and 3. Maybe now I use 1 and 2. If you use 1 and 2, you see here, this is going to be times 2. This is also times 2. Okay, and I know that, okay, if I use ammonia, okay, times 2, because it's to the power second order, right? So if it is going to be second order, so it's going to be 2 to the power of 2. It means times 4. It must be times 4. But let's see, is it only times 4? Okay, related to ammonia. Okay, so 2.05 divided by 0.256, I'm going to get 8. So it's not times 4, it's times 8. So it means there is another one which is going to be 2. So that 2 must be coming from here. So you see, this one times 2, this is also times 2. So automatically, this is going to be first order with respect to ClO minus. Okay, there is no other way that I can show anymore. Okay, but this is going to be, the moment you get that, okay, that's going to be the reasoning. The reasoning, please use, okay, whatever way that I times just now. Okay, you need to show the working over here. Okay, explain. Okay, experiment 1 to 2. Okay, 1 to 2. when I do this, okay, this is going to be 8. Okay, so when I double, okay, this is going to be 2 to the power of 2, you mentioned, and then it must be double also. So therefore, I know that this Cl minus is going to be first order or something like that. And then you also explained about using equation, okay, 2 and 3. I found out, okay, that ammonia is going to be second order because of what? You need to mention. Okay, if you don't mention, you're not going to get the mark. Write the rate equation. Yeah, just simply write now. There will be K and then NH3 to the power of 2 ClO minus to the power of 1. 1 no need to mention, just put it there. Use the result in experiment 1. Okay, so they mentioned use the data in experiment 1 to calculate the K. So the rate is going to be 0.256. K. Concentration of ammonia is 0.1 to the power of 2. Concentration of ClO is 0.2. So K is going to be 0.256 divided by 0.01 times 0.2. Okay, 0.1 to the power of 2 is 0.01. 0.256 divided by 0.01 times 0.2. I will get the K as 128. 128. Okay, let me check the answer. Okay, this is going to be 128, and then the unit. Okay, this is correct. The unit. Okay, so this is going to be 0.256 is going to be mole per dm cube per second, and this one is going to be, okay, to the power of 3. Okay, so mole dm negative 3 to the power of 3. Cancel this, then left with 2. So I'm going to have mole negative 2 dm positive 6 per second. Okay, that will be the answer. Next, on the axis, sketch a graph to show how the value of K changes as the temperature increase. K changes, only K will change when temperature changing. Okay, so rate constant, okay, they will increase. Okay, it's okay. Victoria's internet is bad. Later, I'll pass her the video. So the rate constant, okay, they will increase as the temperature increases. You can write down, okay, you can draw this graph. Or, okay, you can also draw, they do accept a curve. As long you can show that it is increasing with temperature. Okay, as long you show that it is increasing with the temperature. So it doesn't matter, it's going to be straight line or it's going to be a curve. Okay, it doesn't matter. Now, B, in another experiment, the reaction, okay, is going to be between chloride and iodide ions. This one, please be notice this. A solution of iodide ions in aqueous alkali was added to large extent of chloride 1 ions. So do remember last time I told you, in when you want to investigate only one particular ion involved in the rate equation, so we need to use another ion which is going to be large in excess because we want to make it to become constant. Okay, so they are mentioning this one is constant then, and I minus was measured at regular intervals. So now we want to measure the concentration of iodide, okay, iodide versus time because regular intervals. So you plot a graph, okay. So describe how the results can be used. So you get a graph, okay, concentration of I minus versus time. Once you get that graph, they say the confirm to confirm is first order. So if you want to confirm something, concentration versus time, okay, if you look at the graph, concentration versus time, there are 3 types of graph. One, it's going to be like this, okay, and that is going to be 0 order reaction. And there will be 2 graphs that will be curved like this, okay. One of it will follow the half equation correctly. It means the half life is going to be constant, okay. So the constant half life is first order, okay. The half life that is non-constant is going to be second order. So it means now you want to find out that this is going to be whether it's going to be first order. First, you need to mention you are going to get a curve. Okay, you will get a curve, And after that, if you measure the half-life, you are going to get a constant half-life. Okay, and that is going to be enough to confirm that the reaction is first order with respect to this. A three-step mechanism is shown. So you see there is going to be a mechanism over here. Use this mechanism to deduce the overall equation. This one quite easy because they don't ask you to find out which one is going to be the slow step. Okay, because the slow step is going to be the one that we will use, okay, to tell that, okay, this is going to be involved in the rate equation and so on. But you can see here, roughly, okay, if I ask you to suggest the slow step for this reaction, you can roughly suggest the slow step because we know that the rate is going to be related to ammonia and then related to ClO minus. So if you look at the ClO minus, the ClO minus is only going to be involved here. And then, okay, but they say also chloride and iodide. Yes? So this one is different. Yeah. So it's chloride and iodide. Then they say it's going to be first order to I minus. So when I see first order to I minus, if I want to predict which one of these is going to be a slow step, the best prediction will be step number 2. Okay, step number 2 is the best prediction for the slower step. Why? The slower step must be having the one that has the one involved in the rate equation. So I minus is here. So that is going to be the slowest step. So if they ask, okay, but they didn't ask, okay, they didn't ask. So what they are asking now is going to be, they are asking us to use this mechanism to deduce the overall equation. This is very easy. This happens in 3 steps. So add all of them and see which one is going to be cancelled with each other. You see this one will be cancelled if you add. And then you can see water, left and right, they will cancel. HIO, they will cancel over here. OH minus, they will cancel over there. So leaving this behind, so ClO minus plus I minus to give you Cl minus plus IO minus. Very easy. Okay, this is going to be using the mechanism. Identify a step that involves a redox reaction. So this one, I end up calculating. Yeah, we need to calculate. Okay, so the calculation, when I do the calculation, the oxidation number is going to be -1. Okay, I just straight away go to step 2. Okay, to save time. Okay, so I calculated, and then this is -1, and I know this is -1. So I need to calculate for HClO. So easier if you put it as ClO minus. Okay, H plus ClO minus. So I just want to calculate for X over here. X plus -2 equals to -1. X equals to -1 plus 2. So it's +1. So this one is going to be +1. So you can see Cl from +1 to become -1. Okay, so there's going to be reduction. So let's calculate for this I over here. So similar, H plus, so IO minus. Okay, so if this is X, X minus 2 equals to -1, X equals to -1 plus 2. So you get +1. Okay, so this is +1. So from -1 to +1, so it's oxidation. So I know oxidation and reduction. So I found out that step number 2 is going to be redox. Okay, identify one step and explain. So you explain. Okay, step 2, and you need to explain I minus to become HIO. So it's going to be -1 to +1. And then you mentioned about HClO to become Cl minus. Okay, so from +1 to become -1. Have to mention. Okay, that is going to be giving you the 1 mark. Okay, it's done for today. Okay, so now, so for question number 6, okay, complete the table by placing one tick in each row to indicate the sign of each type of energy under standard condition. So here, okay, we can see the bond energy. You need to break bonds. Okay, so always needs to be broken. Okay, so therefore the bond energy is going to be always going to be positive. It's always going to be positive. And for enthalpy change of formation, it depends. Okay, it depends. So it can be either positive or negative. So there are certain things that you need to memorize as well. Okay, lattice energy. Okay, I'll put it over here. Lattice energy is always negative. Hydration energy. Okay, hydration. Okay, enthalpy of hydration is always negative because forming of bonds. Other things, like for example, when you are going to do neutralization, combustion, okay, all this neutralization, combustion will be always negative as well. Okay, maybe these are the things that you want to memorize. Okay, but now if going further, explain what is meant by the term enthalpy of atomization. Enthalpy of atomization is when you are going to form 1 mole of gaseous atom, okay, from elements in its standard state. And you can see here, okay, this is one example of enthalpy change of atomization. You can see Br2 at standard state at 25 degrees Celsius, Br2 is going to be liquid. So you have to put liquid, and then it's going to be, in this case, this is going to be 2 enthalpy of atomization, because they are not forming 1 mole, okay, they are forming 2 moles of Br. Okay, so it let's if I continue C, okay, the overall reaction of atomization is given, okay, and then we need to construct an energy cycle to represent this, and then use your cycle and then calculate the enthalpy change of vaporization. So you see what I did was I rewrote this, and I know that this is going to be 2 times of atomization. So first of all, since they are asking for vaporization, it means I want from liquid change into Br2 gas. So this is enthalpy of vaporization. And I also need to convert the Br2 gas, okay, into atom, okay, which is going to be like I want to change the Br2 into atom, but again it's going to be gas to gas, so it's not atomization. Okay, so this is going to be breaking the bond energy. So I put the bond energy. It's still 1 bond energy because you're breaking Br and Br, so you are going to get 2 Br. So when I this one, I can get the data from the data booklet. You can go and have a look at the data booklet, and you will be able to get the information over there. Okay, I'll continue again. Yeah, so you will be able to get the information over there. So 193, and then we just need the enthalpy of vaporization. Okay, so we know the atomization is given. Just use the formula clockwise equals to anti-clockwise. Okay, just use the Hess's law. So I just put, okay, 2 times enthalpy of atomization is going to be enthalpy of vaporization plus bond energy. So once I get that, okay, I'm going to get the positive 31. Okay, this is quite easy to calculate. Now, suggest how the enthalpy of vaporization of iodine, okay, would compare to enthalpy change of bromine. Explain your answer. Okay, this one is quite simple. Vaporization, you are trying to break the bond between the molecules. So we are talking about intermolecular forces. Both of them are, okay, non-polar. Okay, so we need to tell, okay, which one is going to be greater. Okay, because I2 is bigger, okay, therefore enthalpy of vaporization of I2 is bigger than enthalpy of vaporization of Br2. Why? Okay, because I2 is a bigger molecule, you can say that they contain more electrons, and therefore, okay, they have bigger van der Waals forces of attraction. Anyway, it's only 1 mark. Okay, but if you need, if you want to get the entire 1 mark, you need to mention about the van der Waals forces, and also you compare. Okay, that is going to be important. Now, next is going to be explain what is meant by enthalpy change of hydration. This is also important. This is the energy change when the 1 mole of gaseous ion dissolve in excess water. Okay, this is going to be gaseous ion dissolve in excess water. Okay, let me see whether, okay, my internet connection is quite weak. Okay, so anyway, okay, if I continue, okay, this is directly from your textbook, you can get the information. Okay, suggests why enthalpy change of hydration of Br minus is more exothermic, okay, than of the I minus. We know hydration is exothermic, but now I want to know why Br minus is more exothermic. Okay, the reason why it is more exothermic is, okay, because the Br minus, okay, they are they are smaller, okay, and since this is going to be ion, so you just say Br minus has smaller ionic radii, and because it is smaller ionic radius, the attraction of the nucleus, okay, of the Br minus, they are going to be much more stronger, okay, to the water molecules, okay. So they are going to be, since it's smaller, so there will be more formation of the bond. Okay, the bond that we are going to talk about is going to be, this is going to be ion, and this is going to be, they will have dipole. Water has dipole. That's why we call it ion dipole attraction. Okay, so it's not dipole-dipole, it's ion dipole attraction. So the ion dipole attraction is going to be stronger because the Br minus is smaller. Okay, therefore, okay, it's more exothermic. Okay, if you put in comparison to I minus, okay, I minus is bigger. Okay, when I minus is bigger, okay, if you want to have the ion dipole, this is ion, so the ion dipole, this is delta negative, delta positive. I think in a better way, I think we should draw it in this way if they ask you to represent. So this is delta positive, this is delta negative, so this is dipole, and then the attraction between ion and the dipole is going to be weaker. Why? Because, okay, there is going to be a larger radius. Okay, the nucleus is further away. Okay, so therefore, okay, it's going to be much more, the attraction is not that good. Aneta is asking, can we say it's because of the charge density? Not really, because hydration, okay, involves about how well it can form the bond. Okay, so not related to charge density. It is more towards the distance, okay, of the dipole and the ion. Okay, so if the distance is greater, therefore the attraction is not going to be that strong. Okay, so if it depends, okay, if you have a smaller ion, then the attraction is going to be bigger. Okay, so the hydration energy is going to be more exothermic when they join together. Okay, so it depends on the radii, okay, ionic radii, so not related to the charge density. Okay, we are not looking into the charge density, it's more towards the distance. Okay, distance, whether they are going to be able to form better bonding, okay, between the dipoles of water. Okay, now if you move on, okay, number 7, okay, benzene can be converted into cyclohexane. Okay, so I wrote down, okay, this is benzene and then this is cyclohexane. So it looks like all the double bond are broken. Now this one, okay, when we learn about benzene, we didn't learn about this, but we have learned this under the reaction of alkene. Okay, so therefore they are asking us, for this reaction, name the reaction and identify the region and condition needed. Okay, see, even though we don't learn about this, okay, you need to know that, okay, if you have somehow, okay, like there are double bonds, but those are proven they are not double bonds. Okay, there is going to be a possibilities. I don't think so it was covered in the textbook, so we didn't learn about this. But since this is a 2019 paper, okay, please have a take note. Okay, benzene will undergo hydrogenation. Okay, hydrogenation, and the conditions, okay, are going to be the same as the one that is one that we memorized last time. Okay, I think for alkene, the condition is going to be nickel catalyst 140 degrees Celsius. That was for alkene. Okay, so now it's almost the same. Okay, we are going to use hydrogen gas, nickel or platinum catalyst. Okay, so the condition they didn't give, okay, but you can write down the condition if it is going to be 140 degrees, because we know that benzene, okay, they are kind of unreactive. Okay, so therefore I think better, even though you use the catalyst, I think better also include the 140 degrees. Okay, but they didn't give this in the marking key. Okay, so this is something that you want, maybe you want to take note. Yeah, we have learned under alkene. Now state the bond angles in benzene and cyclohexane. Now bond angle in benzene, because we need to we know that benzene are planar molecule. Okay, planar molecule means we only take the carbon bonded to 3 bonds, even though, okay, carbon normally supposed to have 4 bonds. Okay, one of the electron is delocalized, so it looks like 3 bonds. So for 3 bonding pair, it's going to be 120 degrees. Okay, so the bond angle in cyclohexane is going to be, cyclohexane, nobody said that it's going to be planar. Okay, this is non-planar because each of the carbon, they are bonded to 4, there are 4 bonds. So if they have 4 bonds, therefore they are going to have this 109.5 degrees arrangement. So that is going to be each of the carbon, they are going to be having this tetrahedral shape. So explain your answer. Okay, so what happened? Basically, the pi bond, okay, the pi bond, the 3 pi bond, they are going to be converted into sigma bond. Okay, so because there are a sigma bond, okay, there each carbon is going to be bonded. Okay, earlier each carbon bonded by 3, but now each carbon is going to be bonded by 4. Therefore, they are going to have tetrahedral arrangement. So please refer to the marking key. I think the important thing is the pi bond is changing into sigma. Okay. Now next, okay, we have this mechanism. Okay, of we didn't learn about this, but anything that we didn't learn, they will always give like a relationship. Like for example, they say this is similar with nitration. So concentrated sulfuric acid is going to be used in the initial step. Now, even though it is, they mention it's similar, what I want you to know is, I want you to remember, okay, when you use the, when you react benzene, okay, with sulfuric acid, there is a reaction. Okay, even though you didn't learn in your syllabus, because now from the past year paper, you can see that sulfuric acid, they do react with benzene. Okay, they do react with benzene, and it is similar to the reaction with nitration. Okay, similar to that. So you can see how they how the electrophiles are being generated. Okay, they have given you SO3. Okay, they are going to react with the H2SO4. Okay, and then after that you are going to get this. Okay, the the electrophile over here is this one. This is the electrophile. So you need to draw the mechanism. I think drawing the mechanism is quite easy. Okay, so the the arrow will be from the ring to SO3, and then you will have this H, and then from H the arrow will go inside. Okay, do remember this one, the smiley face with the plus. Okay, and then you are going to get this, and then don't forget to put H plus. I don't think so it's required, but I think it's required for this question. Okay, because the H plus, this is going to be you are going to have heterolytic fission happening over there, so there is going to be H plus there. So this H plus, they will join with this HSO4 minus that you have earlier, and this is going to generate the H2SO4. So this is how the catalyst is going to be reformed. Okay, so it means now the reaction that we are going to talk about is going to be, do remember, okay, even though we didn't learn, SO3 can react with benzene with the presence of H2SO4. Okay, so the catalyst is H2SO4. Okay, so this is something extra that I want you to remember. Okay, possible where they can ask you similar to this kind of reaction. Okay, just remember. Now, the next question is going to be, you if you have this compound. Okay, so suddenly the C12H25 is added to the ring. The moment it's added to the ring, you know that it's going to be alkylation. Okay, so regions and condition. Okay, so alkylation, so you need to have as like this is not acyl chloride, this is going to be you need to have the halogenal alkane. Okay, halogenal alkane, generally maybe we can use the Cl. So what we need to do, you just take this one, you include the Cl, and then you need to have a catalyst. Therefore, I'm going to use AlCl3, and then you need to heat them up. Okay, so this is going to be Friedel-Crafts reaction, and the mechanism, okay, Friedel-Crafts reaction is going to be electrophilic substitution. Okay, electrophilic substitution, you're substituting. Okay, so next is going to be when concentrated sulfuric acid is added, dissociation is taking place in 2 stages. I think we learned about this, whether 2 stages, 3 stages. The first one, the dissociation is going to be way better compared to the second and the following. Okay, so the dissociation is going to be decreased. So here they say write the expression. So I wrote the expression, okay, of the reaction. So Ka2, I gave that. And then they say H2SO4 is a strong acid, okay? And then they say that HSO4 is a weaker acid. So suggest the magnitude. If they already give you the clue over there. So suggest the magnitude. The magnitude they say is strong. Then Ka is going to be bigger. And then for stage 2 is going to be Ka smaller. So we know that the Ka1, which is this one, if I represent this as Ka1, Ka1 is going to be bigger than Ka2. Okay, that's it. I think suggest only. Okay, no need to explain. Okay, if they say deduce, okay, deduce or something like that, maybe you need to use some explanation. When suggesting, okay, they need to tell, suggest, and explain in order to explain. So suggest, just give suggestion, enough. Okay, now benzoic acid, okay, is a weak acid. Okay, the pH is given, so I'm very sure you know how to calculate the concentration of H plus. Okay, and then use the formula. Okay, this one is going to be, the assumption is the H plus, okay, and the ion that is going to be formed over here. This one and this one, they are going to be the same. So I'm just assuming this one is the same. So I will assume also the benzoic acid do not dissociate a lot. Okay, so apply the formula and then you will get the answer. Okay, Ka 6.34 times 10 negative 5. Okay, not a big deal. Okay, to apply. Okay, please, but you need to know about the formula. Okay, learn how to remember the formula. Okay, so number 8. Okay, this is what I want to discuss. Okay, if you need to go for your lunch, okay, please go. Okay, but if you want to stay here, okay, just stay. Okay, maybe I will take about less than 15 minutes for this. Okay, it is very important. Okay, so now for number 8, okay, the mass spectrum of compound X, okay, C5H10O2, okay, is recorded. And then it's a very interesting question because they say the peak of M and M plus 1. Okay, so the moment they say peak M and M plus 1, this is going to be M plus 1 is one of the carbon. Okay, in that sample must be carbon 13. And I told you not to memorize the formula, just use the relationship. Okay, the relationship is, okay, one of it is going to be carbon 13 and it is must be always 1.1%. So I just put the relationship 1.1% is one of the carbon from the sample. Okay, therefore is 1. And the peak, okay, the abundance of that is going to be 1.25 because M plus 1 peak. Okay, so this is going to be 1.25. And then normally we use this formula to calculate the N. Okay, normally. Okay, so I just put N over there. Okay, and then times, okay, the abundance of the normal abundance for M, 22.65, then times 100%. So what I do, I cancel the percentage and then I rearrange and then find the N, and the N I will get 5.017, which is going to be 5. Normally the question will ask predict, okay, they give you the abundance, okay, and so on, maybe just a spectrum, and then using the spectrum, and then they'll ask you predict how many number of carbon. But here they're asking you to prove. Okay, so still the same. Okay, still the same. So, but what we need to know is this relationship. This relationship cannot be found from your data booklet. So you need to know. Okay, you need to know. Now this question is very interesting. Okay, very interesting. Okay, even though okay the answer in the marking key is given C3H5O O plus C2H5O. Okay, this is if you are still wondering why and so on. Okay, generally you can use anything, but they didn't specify. Okay, they didn't specify. One of the reason maybe they didn't specify, but let me just show you here. If you have this compound C5H10O2, okay, if you have 2O, okay, 2O in your organic compound, okay, there are certain groups that have 2O in that compound, like for example ester, one of the example, or you can have carboxylic acid, or you can have diol. Okay, but when I calculate the number of hydrogen in diol, okay, you see here, if I have 5 carbon and I have a diol, okay, how many hydrogen can I have? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Okay, so I don't want 12 because I want only 10. Yeah, so I ignore diol. So my based on my initial thinking, I know that it might be ester. Okay, it might be ester and it might be carboxylic acid. Okay, because there is no other clue. Okay, it is fine. Okay, if you assume. Okay, if you assume, because earlier I was thinking, okay, carboxylic acid is much more easier to see. So I just did like this. Okay, I just did this, and then I thought that okay, let's see whether I can break into this. Normally it can break into CH3. So I calculated, okay, one by one. Okay, if I break here, if I break here, if I break here, I calculated and I came to C4H9 and I received 57. Okay, the moment I saw 57, then I think, yeah, it's fine. Okay, 57. So I just put the 57. So I took this one. Okay, I took this one, C4H9 plus. And then if I break over here, then of course there's going to be COOH. Now, when you do this, please remember, okay, please remember to include the plus. One of it must be plus. Okay, one of it must be plus. Another one must be neutral. Okay, must be neutral. So so if you put plus, then they are going to actually have 2 plus over here. So here, just take 1 plus. Now, but the answer key is going to be given in a different way. Okay, so it's fine. Okay, it's fine. Okay, because you can also break this. Okay, you can fragment this. Okay, in a different position. Like for example, you can take it. What they did was they took it in a form of ester. Okay, they took it in form of ester. So what they did was, okay, they have C3H5O. So maybe 1, 2, 3. Okay, so they calculated. Okay, this is C6, C3H5O. So maybe this one. If you calculate like this, okay, this is going to be C3H5O plus. And then remaining 2 carbon, they remaining 2 will be like this, and then O. Okay, so this is going to be, if you join together, then it's ester. Okay, so what they did was, okay, they calculated this one. Okay, and that is going to be also going to be 57. So it's fine. Okay, it's fine. Okay, if you give in this form. Okay, this is the one that they took in the marking key. If you answer in this way, it's also fine. Okay, they didn't specify. Okay, they didn't specify. State the use of TMS and CDCl3, okay, in NMR spectroscopy. TMS is the reference for NMR. Okay, so it's going to be giving you the 0.0, and then CDCl3 is going to be the solvent. Okay, so you just put it as solvent. Now, next, okay, is going to be this one. This is very interesting. Okay, the proton NMR for the compound. Okay, do remember we haven't found out what is the compound yet. Okay, do remember that. So here, okay, I think rather than just focusing, oh, I decided this is going to be ester, I decided this is carboxylic acid, which was my first mistake. Okay, I try to answer based on my assumption. Okay, don't assume. Okay, no need to assume. What you need to do is just refer to the data booklet and also just refer to those numbers here, and also refer to the number of fragmentation, how many fragments you have over there, okay, how many splitting, to answer this question. So here, when I look at my data booklet, okay, do remember we are looking into proton, okay, so don't go and look at the carbon, okay, so it's proton. So when you look over there, you will notice that, okay, at 2.2, okay, this is from data booklet, it is alkyl next to carbon double bond O. Okay, so it's an alkyl next to carbon double bond O. So if I have alkyl next to carbon double bond O, so I'll put like this, C double bond O, and it must be alkyl. Okay, so it can be alkyl, can be CH3, C2H5, and so on. Okay, so what I do is when I look at the 2.2 here, I notice that it is going to be only one peak, and with number 3. Okay, only one peak with number 3. So therefore, okay, this must be directly to CH3. Why? Because 3 same environment, okay, for the hydrogen, 3 same hydrogen environment, and this environment, the carbon next to it, there is no hydrogen. Okay, therefore, okay, there is no splitting. So I make the judgment that this is going to be CH3CO. Okay, I hope you understand how to make this judgment. Yeah. So here we do the same thing as well. Okay, 1.2 and 3.5. When I look at my data booklet, they say that 1.2 is alkane. Another one is 3.5. They say that it's going to be alkyl next to O. Okay, alkyl next to O. And then they didn't say alkyl next to carbon double bond O, it's alkyl next to O. Okay, now I know, okay, the 3.5, okay, 3.5 is going to be here. And then it's going to be alkyl next to O. Okay, so I draw, okay, C, and then alkyl next to O. So maybe I just put O here. And then alkyl next to O. Okay, what is going to be the alkyl? Okay, I need to see. But do remember there are 2. Okay, there are 2. So one of it, okay, because it's 2, okay, because it's 2 environments, so I just put 1H, okay. But there is a splitting, okay, and the splitting is going to be 4. It means the carbon next to it, this is no carbon. So there will be another carbon over there. Okay, there is another carbon over there, which has 3 hydrogen. Why? Because if you have 3 hydrogen environment, okay, then the splitting will be n plus 1. So 3 plus 1. So this one is going to be something related to this. Okay, and if I want to refer to 1.2 is alkane. Yeah, I can see it's alkane also. Okay, so this is going to give me the reason why I selected this one. So you just write down CH3, CH2O. Okay, that is going to be how you identify. Now, another one, okay, I never said it's going to be easy. Okay, for those who have managed to figure out, okay, good for you. Yeah, but for those who are still struggling, okay, please try to do this again and again. Yeah, so you see here, okay, the last one is going to be the peak at 4. When I refer to my data booklet, okay, it is written alkyl next to O. Again, alkyl next to O. It's not double bond O. Okay, so alkyl next to O. So I know, okay, so there will be O here. Okay, next to O, so I'm talking about, okay, maybe alkyl next to O. So I do not know how. Okay, so if I put it here, okay, what will be the possible, okay, possible answer? Okay, so here when I look at 4, okay, I notice that, okay, this is going to be 2 environment. Okay, there will be 2 environment. So the moment I see 2 environment, it means there must be C and then H and H. There's no other way. There is 2 environment. Okay, and then they also mentioned that, okay, they also mentioned that this is going to be a single peak. Now, if this is a single peak, okay, I cannot just simply leave my answer like that. Okay, why? If I leave my answer like that, then there will be another carbon there. Okay, another carbon. And then if there is another carbon, then that carbon might be connected to 3 hydrogen. Okay, so if it is 3 hydrogen, I will not get only one splitting, I might get 4. Okay, so how do you prevent that from happening? This one must be there. Okay, so that's why, okay, this one came over here. CO must be there. Okay, and then CH2O, so this is going to be the proton that they are talking about. Okay, that one we deduce. Now, when reacted, okay, with aqueous iodine, X produce yellow precipitate. So this one, triiodomethane reaction. So it must have CH3. Okay, it must have CH3. And then we know that, okay, based on what we have done, okay, you see carbon double bond and so on. Yeah, we have this. Okay, these are some of the things that I found out. Okay, I found out must have. Okay, so when I see this, okay, I try to relate. Okay, there is C double bond OCH3. So it must be at the end. Okay, it must be at the end. So I put it over there. And I'm still going to, I still need to figure out where I need to put the remaining 3 carbon because it's C5 here. So what I need to do, I need to refer. Okay, this one I already determined. Okay, but I still have the CH3, CH2O. And then I still need to include carbon double bond CH2O. So I need to figure out how am I going to put this, okay? How am I going to do this? Okay, but again, when I see the third, okay, prediction that I have the carbon double bond O, and then I have CH2 and O, okay? So what I can do, there is no C double bond O, new one, okay? So what I will do, I have carbon double bond O, I put the CH2 here. So it means I'm just basically using the third part over here. And the last one, okay, is the one that I include over here, the second part, which is going to be the CH3, CH2O, CH3, CH2O. So once you put them together, you are tying them together as this molecule. Okay, the molecule is going to be like what I've drawn over there. Okay, they have CH3, CH2O, CH2, C double bond O, and then CH3. So this is the molecule that we supposed to get, okay, based on our prediction. And this molecule is nowhere close, okay, to our previous prediction related to this. Nothing to do with this. Okay, that's why I say that you do not need to follow. Okay, no need to follow. Okay, no need to follow. Okay, you can have this in form of ester. You break in form of ester. You can break this. Okay, but again, we predicted it might be ester or carboxylic acid. But this one, you see, this is not even ester and not even carboxylic acid. This is going to be a combination, like it's like let me show you. This is going to be ketone. Okay, it's a ketone, and as well as ether. If they ask you predict the 2 functional group, okay, which they won't ask you to do, okay, because ether is not in our syllabus. But if they ask you predict the functional group or deduce the functional group, one is carbonyl group, okay, which is going to be ketone. One is ketone, but another one is not in your syllabus, which is ether, okay, which is going to be anything that has R and R like this is called ether. Okay, so it's a combination. So anyway, okay, let's continue. Okay, compound W is an ester. Okay, now they tell is an ester. So when I look at it in form of ester, okay, I draw few examples of possible ester. So I came across, I think I can draw 4 examples of ester. Okay, when 4, I think even I draw another one, 5. Okay, I draw 5 examples of ester. So when I draw each of them, okay, they are going to have 2 peaks. It means the proton environment must be only 2. So if I draw using this one, you see 1 environment, 2, 3, 4 environment. So if 4 environment, I'm not going to include this. This is not possible. How about if I have branch over here? So one environment, this is another one environment. So this is one environment. So both of them same environment. Okay, so 1, 2, 3. Okay, so still we are looking for 2. Not possible. I try different combination. Okay, you can try different combinations. So 1, 2, 3, 4. Okay, 4 environment cannot. I did try, okay, with some other combination as well. So I did try. So 1, 2, same. So 1, 2, 3, 3 environments still cannot. So the only way, okay, normally when we approach ester, we say R C double bond O O R. But take note, okay, this R, this part can be because normally we put carboxylic acid like this, okay. Carboxylic acid is this one. So if I cannot put this as H, okay, but this R group, you can put it as H, like what I did over here. Okay, you can put it as H over there. When I put that as H, this is still ester, okay, and I want to get 2. So if I continue to just put another C over here, it doesn't make sense. So what I did, I tried to put more of them together. Like when I put them together, I have CH3, 3 CH3 group, and each of them, they have the same proton environment. Okay, guys, I know it's getting late. Yeah, just let me finish this. Yeah, so once you have that, okay, this is going to be you are going to have one environment, okay, and then another environment, 2 environment, okay, 2 environment, and then the ratio, you see, they have 3, 3, 3, so 9 to 1, okay, which is going to be the same. So this is going to be the one that we are looking for. So suggest the structure. Okay, this is the structure that I will suggest. And then explain what is meant by chiral center. Yeah, must have 4 different groups attached. The carbon must have 4 different groups attached, and suggest structure V. Okay, they say chiral center, right? Okay, and then carboxylic acid. So I put 1 carboxylic acid. This must be chiral carbon. So I try with some combination H and then CH3. So I need to have some more combination. So I try 2. Okay, so you see everything is going to be total 5 carbon, everything will be balanced. So this is going to be the structure for V. So that's the structure. Okay, total mark 11. Okay, that. Okay, so sorry for